Hello friends, Samson Rainey with NASA's Earth Science News team here. In the lead up to Earth Day this year, NASA has been focusing on technologies that are set to transform the way we see and understand our home planet. And happily today we have three such technologies that fit that bill to a T. First off, we're talking with NASA Ames researcher Ved Chirayath, who's invented cameras that can image undersea environments from above. Shayna Skolnik, founder and CEO of Navteca, is working to bring NASA data to life through virtual reality. And lastly, we have Brian Campbell, Senior Outreach Specialist and Education Specialist with NASA's ISAT-2 satellite, which is set to launch this fall and measure the all-important polar ice, among other Earth features. So let's get started, shall we? First up, we've all seen a bird's eye view of the coastline. It's often beautiful, but it's also hard to see what's underneath. But what if we could see underneath to the important ecosystems that ultimately make a difference for the whole planet? Now, Ved, you've invented a technology called fluid lensing. Do you want to describe how you came up with the idea and how does it work?
Sure. Happy Earth Day, Samson.
Thanks.
So I came up with the idea for fluid lensing actually from astronomy, where we're trying to look through a fluid interface like the atmosphere. But I was fascinated to learn that as of 2018, we still haven't developed a way to look through the ocean surface, which covers actually the majority of our planet. So I came up with an algorithm called fluid lensing, and you can actually see in this video what the fluid introduces to light when it casts down upon the ocean. So you'll notice there's lots of distortions caused by ocean waves and the refractive interface between air and water. And there's also the formation of these bright bands of light called caustics. And those really hinder our ability to image from space and from the aircraft to study our largest ecosystem.
So with your technology, what are you able to make out that you couldn't make out before it?
So I like to think of it as having a diver's view perspective without having to do the diving. So from aircraft, we can see in the simulation actually what the result would be for fluid lensing. The raw data shows a lot of distortions. You can't actually resolve the geometry of a lot of things underwater. And the fluid lensing result, which we see in the bottom right, actually shows a 0.5 centimeter resolution picture of that same environment, and this is captured from aircraft. So we can not only resolve objects, but measure them accurately over time.
Now, by aircraft, do you mean kind of planes, or we're thinking of drones that can kind of go pretty low?
Yes, right now we like to fly drones or unmanned aerial vehicles. These are really, they're really quiet, they're electric, and they enable us to map large areas of coral reefs on islands, which are really difficult locations to get aircraft to. So in this simulation, you can actually see what the raw data look like from the aircraft, and you'll notice all the fluid distortions, and then our post-process 3D view of that environment. And this is really the first time we've been able to map the ocean floor at a resolution comparable to a diver and really understand the biodiversity of these ecosystems.
And I'm just wondering let's say how far up is the drone from the surface? Because it looks like we're getting pretty close down to the water, unless it's very clear, and that's why it looks close.
Sure. So here we're actually stripping away the ocean surface and getting a view that really would be impossible to get without this technique, unless you drained the ocean, which we wouldn't want to do, or could do. So here we really can resolve those 3D structures. We're looking at a scale of roughly 20 meters in width, and we're flying at an altitude of 50 meters, but the technology could work all the way up to orbit.
So in other words, what we're seeing is, I mean, the drone is pretty high up, but we're really dialing into a very high resolution right now.
Yes, in fact, the algorithm exploits positive magnification events. When a wave passes over, it'll actually magnify the object, and I use that as a sort of traveling microscope to peer deeper in the ocean system. So not only can we see at higher resolution than the sensor is capable of, but also we can see very deep in the water column, up to about 30 meters.
Great. So, well, currently we're using drones, but the idea hopefully is to have it on a satellite one day, right?
Yes. Right now, I love visiting these ocean ecosystems. They're absolutely beautiful, but as of 2018, we've mapped more of Mars and the Moon than we have of our own ocean floor. We've mapped less than 4% of our odifferent floor. So I think we really need a path to space to start looking at these ecosystems globally and understanding how they're changing.
And can we talk about the difference between flying on a drone and having it be on a satellite? Is obviously a greater area covered and maybe more frequent interval of coverage, right?
Absolutely. These ecosystems are changing rapidly, and so we can't always deploy aircraft to an island to observe how they're changing. It's usually once a year we have time to visit all the different main islands that we like to look at. Satellites don't have that inhibition. They can really target any spot on the globe very quickly and allow us to build up a picture of what's happening in near real time.
Great. I'm always curious about, the Great Barrier Reef is always in the news now, so Traditionally, they do these ground campaigns or water campaigns to get like certain parts of the reef. So I'm guessing by using this technology, we can just get a fuller picture of what's happening and inform like the entire ecosystem that's impacting the reef and how the reef is impacting other ecosystems. Is that kind of the...
Absolutely. Right now, this would be a really great complement to those in situ observations, and you really need both to understand what's happening on a large scale as well as on the finest scales, genetically in corals, as well as the fish that are in the environment. That can tell you a lot about an ecosystem.
Fantastic. Well, Ved, I hope fluid lensing does find its way on a satellite at some point soon.
Thank you.
Great. So from one instrument that is hopefully one day going to grace a satellite to another instrument that is set to launch this fall, ICET-2 is tasked with measuring polar ice and other important Earth features. Now, Brian, I guess first off, what is polar ice and why should we care about it?
So yeah, polar ice is very important to our planet, and one thing I like to start out with is that ice really literally keeps our planet cool. And by that I mean, when there's ice, ice has high reflectivity. It's a white surface. Ice and snow has the same type of it's called albedo. But what happens is that the sun's energy reflects off of that surface, and then a lot of it gets reflected back into space. When that ice isn't there, it gets absorbed by the oceans, absorbed by the land, and therefore heating up the planet. So polar ice, when we talk about polar ice, we talk two regions, the North Pole and the South Pole, the Arctic in the north, Antarctic in the south. In the Arctic, it's basically sea ice, okay? And that's frozen saline or salt water. And that's surrounded by land, like the land of Greenland, the ice sheet, land ice. But then we have the Antarctic, which is land ice or an ice sheet surrounded by sea ice. So it's kind of the opposite, but we're really looking at the polar regions around the coastal areas of the North Pole and the South Pole, where we're seeing a lot of the ice melting over time.
Wow, yeah, we've been seeing a lot of that in the news the last few years.
Yes.
So what instrument is responsible on ICET-2 for these measurements, and how does it work?
So the instrument responsible that's going to be on ICET-2 is called ATLAS. It's the Advanced Topographic Laser Altimeter System. It's a mouthful, but it's going to be an amazing satellite. It's going to be taking 1,000 times more measurements than our previous satellite, which we'll talk about in a second. But what the cool thing about the ATLAS satellite is that it's going to use a laser altimeter system. And that laser altimeter system will send laser photons from the satellite to the ground and then back to the satellite. And we're going to be able to measure to the accuracy of 1/1000th of a second, that open window of when it leaves the satellite, hits the surface and comes back again, in order to map the elevation of our entire planet. And what you're seeing in the video here, you're seeing the engineers from the ICET-2 mission building the actual ATLAS instrument that's going to house the laser pulses.
Incredible. Well, we all know that every time NASA sends out another satellite, we're always looking to improve upon previous ones.
Sure.
And we know that ICET-2 went out from 2003, 2009, gathering similar measurements. Yep. And then we have now the Icebridge campaign, which is airborne and trying to take those similar measurements before this one comes out.
Yep.
So how is ICET-2 going to be different from ICET?
So yeah, it's all about technology. So the ICET-1 mission, as you mentioned, 2003 to 2009, had 3 lasers on board, but it fired a single laser each time. And it fired off 40 laser pulses per second. Back in 2001 and 2002, when it was being built before launch, that was the technology we had. That was, the most modern technology for the laser altimetry. So what we're doing now with this satellite is this satellite on ATLAS, the ATLAS instrument on this satellite will have basically one single laser. It has 2 lasers on board, one to use and one for reserve. The one that's going to be firing down will split off into beams, and you can see it on the video now. It'll split off into 6 beams, and each beam will split off into a pair. So what we're going to be able to do is, unlike the original ICET-1 satellite, which was a single laser pulse, laser beam down, we'll be able to calculate the slope so we can better estimate the elevation that we get. And because of this satellite, ICET-2 will be able to measure 1,000 times, take 1,000 times more measurements than the original ICET satellite. Wow. And what that means is we're going to get about 1 billion measurements every 4.6 hours from the satellite.
Huge data sets being sent back down.
Yes, yes.
Great. Well, of course, as the name suggests, it's ice, it's its main measurement, but it's also measuring other features that are important for scientific research, if we want to get into those.
Sure. So it's ICET-2. It stands for Ice, Cloud, and Land Elevation Satellite 2. And obviously, ice is our primary objective, ice sheets and sea ice. But what we're also looking at, since it's an altimeter and measuring elevation, we're going to be able to map anything on the planet that has elevation, from buildings to landforms like mountains, valleys. We'll be able to look at sand. You can see on the video here, it's showing you the different types of terrain that we're going to be able to measure. Not just the ice, but one of the major things we're looking at is tree and tree height.
Wow. And by getting the tree height, we can kind of estimate to some degree how much carbon is stored in those trees. Is that one of the things?
Right, yeah, so we'll be able to see how, where trees are, photosynthesis pulls carbon dioxide out of the atmosphere. Okay, we want a lot of that out of the atmosphere because it's a lot of it's there. We don't want that in our atmosphere.
Right, right, very important. So in terms of the lifespan of this satellite, what are we looking at?
So we're looking at a minimum of 3 years. And after that, you know, we go as long as we can, as long as everything's working properly, and, you know, sky's the limit.
Fantastic. Well, Brian, wishing ISAT to a long, well-lived life.
Thank you.
Great, thank you. So more on NASA satellites. We know that they're renowned for capturing beautiful images, but they're also bringing back powerful data that help us inform how our planet is changing. But NASA is also interested in seeing how we not only observe, but experience NASA data. Case in point, virtual reality. So Shayna, what is virtual reality, and how are we partnering with NASA to bring that powerful technology to bear?
So virtual reality is an exciting technology that simulates reality through computer-generated images. So when you put on a head-mounted display, like this mobile headset that I have here, you get the impression of being surrounded by a different reality. You're really immersed. And my company, Navteca, works with NASA, with the Science Mission Directorate, Applied Sciences Group, and also with the Headquarters Information Technology Communications Directorate. And we're exploring how virtual reality, or VR technology, can be used for science data visualization. In the past, NASA's really worked with virtual reality for astronauts to train them to go to space. And now we're investigating the technology for Earth science, especially looking at data that's used for disaster applications, so hurricanes, fires, and floods.
Great. So what are the key technologies that make VR possible right now?
So we're using commercial off-the-shelf hardware. That means you can go out and buy it yourself at a store or online. We use both the immersive systems that use positional tracking and hand controllers, and also mobile headsets. We use software for the GIS, geospatial data, and we even use gaming engines to do the software development. So what you're seeing here on the screen is a demo that we created using 3D data from one of NASA's satellites called Global Precipitation Measurement. And the advantage that VR brings to that is you can actually go down inside the data set itself and look around. When we look at the Earth on a flat surface, like a piece of paper, a map, or a screen, we often see the size and shapes of the continents and the polar regions distorted. But VR gives us that spherical environment, so it allows us to see the planet in a more natural way.
Cool. Well, let's drill into the kinds of NASA satellite data that you're looking at right now and working with.
Yeah, so in addition to GPM, we work with all kinds of different satellite data, also model output data, so data that's been processed on a supercomputer like Discover at NASA Goddard Space Flight Center, and different types of geospatial data that focuses on disasters. So in this image that you're seeing, this is a 3D model that Navteca produced of San Juan, Puerto Rico. And we were looking at the impact of flooding from Hurricane Maria, and then also simulating flooding at different category hurricanes. So by focusing on these natural disasters, we're helping to develop enhanced decision tools to help people use data to make better decisions.
And I can see that you can kind of figure out how far in the flooding reached and do other kinds of post-storm analysis and research.
Yeah, virtual reality gives you a really different view. It gives you a sense of scale that you don't have when you're just looking at it on a flat surface. And also, it's a really different way of looking at data. So instead of just looking at numbers, then you can actually go down and experience what it feels like to see 2 meters of flooding, and you can see what that looks like on a building and understand the impacts from that disaster better.
Amazing. Well, my next question was, is it actively being used? And it sounds like it is being used for a lot of post-data analysis.
Yeah, all of our work is still experimental. We're really pushing the limits and trying to see how the technology can be used. But I can definitely envision a day when we will use both virtual and augmented reality technologies for these kinds of practical applications. So whether it's scientists going down and exploring 3D terrain and seeing the data overlaid on top, and even interacting with it with their voice and gestures, or an augmented reality like a heads-up display. So you could have data that is coming to the windshield of a vehicle. So people who are doing first responder activities could actually get information in real time at that disaster scene.
Wow, a lot of potential there. So I guess one of the challenges is just because so much data is coming in real time, being able to process that and have it available to use maybe during an event or somehow for disaster management in real time.
Yeah, absolutely. And that would be fantastic if we get to that point.
Great. Thank you, Shayna.
Thank you.
Well, we have time to go to your questions, so please feel free to shoot us a question in the feed below and we'll get to as many as we can. I think we already have a few that came in here. I think we have a good one. For Brian, how will ISAT-2 be able to measure sea ice thickness?
Yeah, so we're going to be able to measure the sea ice thickness, what's also called sea ice freeboard. So it's that difference between the surface of the ice to where it touches the surface of the water that it's underneath. So it's that difference, and that we can measure that elevation using this altimeter system. The other ice, like the land ice or the ice sheets, since we're an altimeter and we're bouncing laser pulses off the surface, we're not penetrating the surface, we won't be able to get the thickness of that really deep ice, that land ice. But what we're doing is we'll be able to create digital elevation maps, and through this over time we'll be able to see the elevation changes, which will help us create, more understanding of what's happening to the ice.
Great, great. Well, Shayna, this is a nice cross-pollination. How could virtual reality be used for something like ISAT-2 data?
Well, as you just heard Brian discussing the 3D terrain and all of that mapping, that would really come to life in virtual reality because you would get a sense of the scale, the depth, the altitude, and then being able to overlay that ISAT data, the point cloud data, so those volumes on top, and really be able to explore that instead of layers or slices, but actually be able to go in and explore that. We could potentially get a different perspective on the data. It'd be a cool collaboration.
Wow. Yeah, so you can fly through these data sets because you're traversing through so many hundreds of miles in just like a click, just a turn and a...
Yeah, and VR actually gives us a really cool impression of the fourth dimension of time. So you can really fluidly move through a data set and see how changes occurred over the passing of time. It's a really different way of looking at data.
Amazing. Thanks, Shayna. Well, here's one for Ved. Does fluid lensing measure under the ocean?
Under the ocean. Well, for shallow regions, we can map down to about 30 meters depth. And actually, if you just look at the total area of Earth that's covered in less than 30 meters of water, it actually exceeds all the land area. So there's a huge amount of environments we have yet to really see. And I am also excited to perhaps use VR to explore some of those environments.
Wow, interesting. Let's see here. That's interesting. Could we launch an army of drones to measure and map the entire ocean system? It's been too long for humans to get this accomplished. What is your thought about that strategy?
I would love that. I think we live in a very unique time in that if you open your phone and you zoom in on satellite data, it's usually NASA data or commercial data. The minute you get into water, it just looks blue, and our planet from a distance is blue. There's no reason why we shouldn't be mapping these things.
Great. Let's see. Here's a VR question for Shayna. What about VR for home users to fly assistance drones to disaster areas? What do you think of that idea?
Well, that would be really interesting to use VR for that. There's already some cool applications out there that you can try, for example, exploring the surface of Mars and other things that NASA has put out there. In terms of using VR to fly drones, I guess the sky's the limit. The technology will really continue to improve, so the hardware will become more sleek and we'll see more and more functionality evolving.
Great. That would be so interesting to have a virtual reality headset on and have that relay commands to drones.
Yeah, and that's actually something that we're seeing other agencies that do direct disaster response looking at, is maybe you could have an incident command manager with a virtual reality headset getting a 360 picture of a scene with all kinds of different data streams coming in, and then sending that data back to the field, maybe as an augmented reality display, like the heads-up thing that I was mentioning earlier.
Cool, incredible. Thanks, Shayna. Here's a question from Paul Fulcher. He wants to know, These things are coming in quick. Sorry. No, Harold Peters. Paul just asked the question that you answered, Shayna.
Good question, Paul.
Harold Peters asked, how does ICET-2 laser respond to fluids?
So yeah, since it's laser light, it's going to hit the, when it hits a fluid, hits the water like a reservoir or a lake or the ocean, you will get some refraction. So what we're doing with the satellite is we are just measuring those laser pulses that hit the Earth's surface and come straight back up. So the movement of water will have an effect on this. You will get refraction, but the ones that do reflect off the surface, those are the ones that we're really looking at. And really smart people at NASA have written algorithms to figure out what happens in all these things that are in motion.
Wow. Speaking of algorithms, and it's a scare word for a lot of people, including me, but how does the algorithm work with your fluid lensing? Like, what is it? How did you figure out these algorithms to make this happen? Like,
sure, that was the subject of a 5-year doctoral degree, so it took a while, but that's a good question. It actually, if you think of how your brain operates when it looks, let's say you're looking at someone underneath a swimming pool, your brain has no trouble figuring out the shape of their face. They can probably sketch the individual very accurately, and yet, we don't do any computation. So what we're relying on is intuition, relying on knowledge of the fluid surface. Fluid lensing does a very similar things. It creates a fluid model. We know that water can only take on so many shapes. It's actually very unique on Earth that we have the right parameter for gravity and water's viscosity to create natural lenses. This wouldn't occur if, for example, the oceans were filled with honey or a different fluid. So that's one method, and then the rest is a lot of computer vision to track those bright bands of caustic light that go underneath.
Mind-blowing, and thank you for answering in a way that I can understand. That was your best shot. And you did well, thank you. Looks like we have time for one last question. Let's see, how can ICET-2 help in studying the land topography to solve the vegetation and soil erosion / degradation problems? Okay,
yeah, that's a great question. So, of course, since it's an altimeter, we're going to be measuring everything. So we're really going to look at tree heights. We're going to be looking at, we're going to create digital elevation maps of vegetation across the planet. Okay? All of NASA's Earth observing satellites work in tandem with one another in the sense that they're measuring different things. So for instance, we have the Global Precipitation Measurement Mission, and that's looking at lots of things, whether something's in there are landslides and erosion and all that stuff. So when we get the data for digital elevation maps of trees and things like that, vegetation around the world, we will work with the GPM community to figure out how we combine that data with the landslide data with what some of the scientists are working on.
Incredible. I think that just shows the ways that data from one satellite can really complement and help all the other Earth-observing satellites that we have up there.
Yep.
Great, thanks, Brian. Well, believe it or not, that's all the time we have left, and it seems to have flown by. We hope you learned a lot about some of NASA's up-and-coming Earth science technologies. And if you would like to learn more, please check out the hashtag NASA4Earth, NASA #4 Earth online. Thanks for joining, and have a great Earth Day.